Good evening to all. I'm Sandhya, a PhD scholar from IIT Kharagpur. I would be taking these NPTEL live sessions for payment material course on every Monday evening 6 to 8 p.m. During this 2 hours of live session, would be discussing about uh, mainly three parameters. One is would be covering the summary of last week's sessions. We could have gone through 5 lectures that have been assigned for the last week. Those 5 lectures would be summarizing in 2 to 3 minutes. And in those 5 lectures, whatever the possible numericals that would be solved in these 2 hours of live session. And in addition to that, if you have any further questions and clarifications that need to be done, as far as the previous week sessions are concerned, we would be discussing on them also. And also regarding the numericals that we are being solved during the live sessions, any clarification regarding that would also be discussed. And in addition to that, if you have any further questions, you can still post them in the forum. I would be replying there. And as we move to the another week, usually we will be solving the assignment questions of previous week. Today we will not be solving because you have a deadline till Wednesday to submit your assignment one. So once you finish your submission, when I come to the next Monday's live session, I would be discussing your previous assignment one solutions also. So let us start with the today's live session. And meanwhile, if you have any questions during the session, you can feel free to type your questions in the chat box, and you can raise your hand also. I can unmute you so that you can ask your questions. And also, while I am solving the questions, please be ready with a paper and pen. So, along with me, you would be solving them, and I will be asking the answers from you. You can type in the chat box, and we will be discussing about those solutions. So, as far as the 5 lectures are concerned, in the first lecture, we have studied about introduction to soil as a highway material. So, all the materials have been introduced, and the importance of soil in the pavement construction has been introduced, and followed by lecture 2 and 3, where the particle size distribution has been given main concern. And as far as the coarse aggregates are concerned, how do we do the sieve analysis? And when we come across fine aggregates, when they are passing to 75 micron, how do we go for sieve analysis? Do we really do the sieve analysis? Then we have discussed about the hydrometer analysis, why it is important for fine grained soils to go for hydrometer analysis instead of regular sieve analysis for the coarse aggregates. And also we have been introduced with the Stokes law. When we are taking the hydrometer readings, so what are the types of corrections, meniscus corrections, temperature corrections that have been done, and these are the minimal are areas that can have a possibility to have some numericals. So I have highlighted here. And in the lecture 4 and 5, we have been discussed with the consistency limits and the classification of soils. As far as consistency limits are concerned, the Atterberg limits has been introduced, liquid limit, plastic limit, and shrinkage limit, and how with the addition of water, how soil can move from solid state to semi-solid state to plastic to liquid state, and at each state how the particular water content is what we have defined as liquid limit, plastic limit, and shrinkage limit, and how the shear strength would vary at those boundary points that have been discussed. And in addition to that, when we enter into the classification of soils, the classification of soils according to the ASHTO classification, how to determine the group index, why do we use the group index in the first place, and how to classify the soils based on unified soil classification system, based on Indian the standard classification system that has been discussed, and the difference between unified soil classification and IS classification system that has been discussed. So these are a few of the major areas. So you will still have a probability to get some numerical. So I would be starting from few basic questions and involving the concepts because the participants involving are from undergraduate to various wide variety of regions as far as the field is concerned. So let me start with the first question. The first one is which of the following soil is the alien soil? So we have different type of soils based upon the way they have been formulated. For example, there are a few soils which have been transported from one place to the another place. So we know how the weathering action has been done from bigger rocks to the smaller size aggregates, and when the aggregates have been decreased to the smaller size, how they have been transported from one place to another place. This can be done through different mediums, like water can be some medium at some places, wind can be another medium, and glaciers can be another medium. So based upon the type of medium, soils can be transported from one place to another place. These are actually called as transported soils. And there are a few type of soils where they have been formulated at a particular place, maybe according to the vegetation that has been placed at that place, and after particular years that could have been converted into the soils. So there are residual soils, there are transported soils, there are weathered soils, soils that have been disintegrated with the time, and there are volcanic soils. So these are the soils which have been formed from the volcanic ash. So here the question is, we have aeolian soil. So this soil is which type of soil? Aeolian soil is basically a type of transported soil. So this transported soil is basically through one type of medium. What is the type of medium that we will see? Usually wind is the type of medium here. So through wind, this soil has been transported from another place to one place to another place. So this is a transported soil. And when it comes to the lacustrine is another type of soil, just like aeolian soil, and these are deposited at the bottom of the lake mostly. So through lake water, they move from one place to another, and when it reaches to the bottom of the lake, they get deposited. And the alluvial is another type of soil, and these are transported by running water. And aeolian, as we already know, this is transported by wind. And there are another type of soils which are called as marine soils, and these are deposited in the seawater. So which of the following are true? So in this question you can see I have given three options. Let us discuss each option one by one. At shrinkage limit, the soil remains fully saturated. So whether this is true or false. To understand this, let us say we have liquid limit, we have plastic limit, and we have shrinkage limit. So shrinkage limit, let us say you have soil, and in between soils there will be air voids. So when you keep adding water to this, initially what happens? Water will go and fill into the air voids. So you can still add water until the air voids is filled. So that means until the entire soil gets saturated. So that limit is actually what called as shrinkage limit. So at shrinkage limit, what happens? There will not be any change in volume, and there will be a full saturation in the soil. But beyond the shrinkage limit, when you keep adding, that's when actually soil starts to change its form from solid to semi-solid, then to plastic, then to the liquid state. So the first option, which is saying at shrinkage limit the soil remains fully saturated, is true. And the second option is the shear strength of all soils at liquid limit is the same. So what happens at liquid limit? As you move from plastic limit, when you keep adding a little more water, so the entire soil mix with water doesn't have any strength. When I say it doesn't have any strength, when you apply a load, it is like a slurry. It cannot take more strength. So it won't be completely slurry, but it will not be in a thicker state. The consistency is very smooth. So at that time, the shear strength of all the soils would be mostly zero. So the shear strength of all soils at liquid limit is usually zero. So that is same. So the option D is also true. Coming to the option C, the shear strength of all soils at plastic limit is the same. So what is the plastic limit? So all these limits are particular water contents. When I add particular water content and when I try to take some amount of soil and try to roll it into 3 mm thread, at particular water content, what happens was that thread tries to crumble or try to make a crack, and that particular water content we call it as plastic limit. So the water content at which it tries to crumble or it tries to crack will not be same for all soils. It changes from soil to soil. So the shear strength of soils at plastic limit is usually not same. It is different. So the option C is not true. So you can see option A and B are the true. And I think you can solve this question on paper. So there are two types of clays I am giving. One is clay A and one is clay B. So for clay A and B, I have given liquid limit and plastic limits. So there are two questions. A, which clay would undergo larger settlements under identical loads? And the question B is which is more plastic. So let us discuss about the first part in the first place. If I want to understand which clay would undergo more settlement, we might need to understand which clay would be more compressible. So in order to understand which clay is more compressible, I need to know whether the particular clay will fall into low compressible region or high compressible region or intermediate compressible region. If I talk about it, if I talk about the unified soil classification system, there will be only two categories. One is low compressible region, another is high compressible region. But if you talk about IS classification system, you will have low compressible region, intermediate compressible region and high compressible region. So this classification usually depends upon liquid limit value. So in the US classification, what happens? When the liquid limit is less than 50, we call it as low compressible. When it is more than 50, we call it as high compressible. So if you take according to the US classification, clay A has a liquid limit of 44 and clay B has a liquid limit of 55. So clay B is actually having liquid limit which is more than 50. So that means clay B into the high compressible and clay A into the low compressible region. So when I say the clay B into the high compressible region, when the load is applied, it has higher probability to compress, thereby it is in high compression zone, so it will be undergoing more settlement. And when it comes to the another part which is more plastic. So in order to determine whether the material is more plastic or not, so usually we do not prefer the soils with more plastic state. So we wanted that to be as low as possible. So if I wanted to determine which are more plastic, the parameter that we use is plasticity index. So plasticity index, how do we determine? Plasticity index is the difference between liquid limit and plastic limit. So if you see for clay, what happens? For clay, liquid limit is 44, plastic limit is 20 and the plasticity index would be 44 minus 20 which is 24. And for the clay B, in the same way 55 minus 35 that would be 20. So if you could see plasticity index for A and B, plasticity index for A is more. So based on this, we can say that A is more plastic than the clay B. And if you could see this problem, if the proportion of soil passing 75 micron is 50% and liquid limit and plastic limit are 40%, 20% respectively, then the group index of soil is. So this group index is usually we would use in ASTO classification system, and you know the minimum value for group index should be 0 and maximum is 20. At any time, if you get the group index value in negative, you have to represent with minimum 0, not the negative value. So if you could see the formula I have mentioned here, group index value is 0.2 into A plus 0.005 into AC. So you have some unknowns to be determined before calculating the group index. So A, B, C, D. So let us see what are those A, B, C, D first. So if you see the A equal to F minus 35. What is F here? So if we have the percentage of soil that is passing 75 micron, let us say here the percentage of soil that is passing 75 micron is 50%. So 50% minus 35. So here that F is percentage of soil passing 75 micron. 50 minus 35 is 15 it will be. In the same way here F you can substitute as 50%. And if you come to the C includes WL, which is nothing but the liquid limit. So liquid limit is already given here as 40%, and IP is nothing but the plasticity index. So how do we determine the plasticity index? Plasticity index is the difference between liquid limit and plastic limit. So it would be difference between 40 and 20. So now we know all the unknown parameters. Let us substitute. Now you can calculate ABCD. Once you know ABCD, we just need to substitute them into the group index formula, and then we will get the group index as 6.5. Okay. So if you see the sixth question, the coefficient of curvature is 1.4, which is nothing but CC. D30 is 3 mm, D10 is 0.6 mm. So based on the information of particle size distribution for use as subgrade, this soil will be classified as. Currently in the problem, they have given coefficient of curvature D30 and D10. They are asking that what is the type of soil it is. So we know that we can define the soil type initially. We need to define whether they are coarse particles or not. For that, what we do? Usually, we have a, let us say, 5 kgs of soil. We will be sieving through 4.75 sieve, because 4.75 sieve is the sieve which would differentiate differentiate the soils whether they are actually coarse or not. Let us say, if the particles that are retained on 4.75 are more than 50%, you can tell them as gravel. Then if the particles that are retained on 75 micron are more than 50%, you can tell them as sand. So if the particles that are passing 75 micron are more, then you can define them as fine aggregates. So initially let us define whether they are sand or gravel. Anyhow in the options everything is given as sand. So to define whether the particular metal is sand or not, what do we need to do? We have to sieve through 75 micron sieve and see if the materials retained on 75 micron are more than 50%, then we can say them as sand. That is one classification that we can do. In addition to that, let us say if they are sand, whether they are well graded or poorly graded sand, how do we define? So for that we have coefficient of uniformity and coefficient of curvature. These are the two parameters that would be used to define whether the particular kind of soil is well graded or poorly graded. So if Cu greater than 4 and Cc is in between 1 to 3, we call them as well graded. If the Cu greater than 6 and Cc is in between 1 to 3, we call them as well graded sand. So let us see here. So now CC is given in the problem. So no problem. CC is in between 1 to 3. So but based on this you cannot directly tell they are well graded or not. So you need to also determine how much is the Cu value. If you want to determine Cu value, what is the formula? D60 by D10. But currently we know only D10. We do not know D60. How do we determine the D60? They have already given the coefficient of curvature. You know the formula for coefficient of curvature as D30 square by D60 into D10. Just substitute these values into that, then you will get the D60. So once you get the D60, we have to substitute D60 by D10. You will get the Cu value. And if the Cu value is more than 6 and Cc is in between 1 to 3, then you can tell that the particular soil type given is well graded sand. And if you see the next question, In a soil specimen, 70% of particles are passing through 4.75 mm Indian standard sieve and 40% of particles are passing through 75 micron sieve. Its uniformity coefficient is 8 and the coefficient of curvature is 2. So as per IS classification, this soil is classified as. So what have been given? There is a 4.75 sieve and they are telling that 70% is passing through that. There is a 75 micron sieve and 40% is passing through that. So what is the type of sieve? Let us say if you want to determine what is the type of soil, you need to understand what is the percentage of amount that is retained on 0.075 mm and also 4.75 mm. If the amount of soil that is retained on 4.75 mm is more than 50%, then you can tell that as a gravel. If the amount of soil that is retained on 0.075 mm is more than 50%, then you can call it as sand. But currently you have only percentage passing. So let us say determine what is the percentage retained. So the percentage retained on 0.075 mm is 60%, which is more than 50%. That means one thing that has been clarified is this is a sand. 60% is retained, so it is sand. And what is the Cu? Cu value is 8. That means it is more than 6. And what is the Cc value? In between 1 to 3. So it is a well graded sand. Okay. These two are used to determine whether they are well graded or not. And the 60% is used to determine whether it is sand or not. So this is a well graded sand. And you can you can see the nomenclature here when I write SW, that means well graded sand. So the major type of soil is sand. But what is the type of sand is well graded. So it says the characteristics of the sand. So you would be writing this as SW and you would be pronouncing it as well graded sand. Let us see and ask the following question. So these are the sizes and this is one type of soil classification. We can see on the left side we have size categories like less than 0.002 mm, 0.075 mm to 0.002 mm and so on. On the right side we have corresponding type of soil. So we need to match what is the type of soil. Let us start from the place where we know. If you come to the option D, 4.75 mm to 0.075 mm. That means the soil that is passing through 4.75 mm and retained at 0.075 mm. Usually we call them as sand from the previous question also. So D would be 2. And if the particles retained on 75 micron mm are sand, then the particles retained on 4.75 mm are gravel. That is also known. C is 1. So whatever that is passing through 0.075 mm is usually silt. But here you can see A and B both are actually passing through 75 micron. If you take the B, first 0.075 mm to 0.002 mm, this you can think as silt because less than 0.002 mm can be clay. So this is the option 5412. And if you come to the next question, a soil mass contains 40% gravel, 50% sand and 10% silt. The soil can be classified as. So what they have given? They have given that we have 40% of gravel, 50% of sand and 10% of silt. So how do we classify this soil? So one thing we all should be remembering is what is the sieve size to determine whether the soil is gravel or not? 4.75. What is the sieve size to determine whether the particular type of soil is sand or not? 0.075 mm or 75 micron. So when I say 50% of sand, that means 50% of soil particles are retained and 75 micron. When I say 40% of gravel, 40% of particles are retained and 4.75 mm. And when I say 10% silt, 10% of particles are passing through 75 micron. So you can see here, this is a 4.75 mm sieve, 40% retained, 50% retained and 75 micron. and 10% is passing to the silt. So if you see the options, there are two types, A, B, C, D, two possibilities. One is silty sandy gravel or gravelly silty sand. So first we have to confirm the given soil is either sand or gravel. That is one thing we have to confirm. So once after confirming that, we need to determine whether the dominant portion in the sand. So you can see here on the 0.075, and also you can see in few options they also have mentioned the quotient of uniformity value. So you also need to determine quotient of uniformity to confirm your option also. So first thing that can be done is, so the major retaining portion is on 0.075, that you can see. So when the major portion is, let us say 40% is 4.75, 50% is 0.075 and 10% is a silt. What is a major? 50% is a major. So this type of soil is actually sand, that you know. So sand is a type of soil that has been confirmed. So if you we have eliminated the option A and B now, and we can move to the option C and D because gravel is silty sand. So the type of soil is what we write here at the end. So sand, we know sand because the amount of material that is retained is here you can see 50 is retained here, 40 is retained here, it will be more than 50%. So sand is confirmed. Now we have to determine whether that is gravelly silty or not. So how do we write the gravelly silty? So 4.75 is the 40% major portion followed by silt. So you can see gravelly silty sand. So the type of soil is sand in which gravel is the major dominant portion followed by the silt content. Okay. Now let us determine the Cu value. So to determine quotient of uniformity, what do we need? D60, D10. What is D60 actually? So D60 is a sieve size. D10 is a sieve size. But which sieve size? So when I say D60, so for example, if I have a sieve size, let us say 3 mm is my sieve size. So if I have 1 kg of soil, in that 1 kg, when I say 1 kg means 1000 grams, in that 1000 grams, if 60% of this soil particles are passing through my 3 mm sieve, then my 3 mm sieve can be called as D60. So D60 is that sieve size through which more than 60% of particles can be passed. In the same way, D10 is the sieve size through which more than 10% of particles can be passed through it. So here what can you see? So if you see the 0.075 mm, what happened? 10% of particles are passing through 0.075 mm. So we can say this 0.075 mm as the D10. And if you see 4.75, 40% is retained. That means 60% is passing. In that 60%, 50 is retained here, 10 is passing. So we don't need that information. But 40 is retained means 60 is passing. Okay, so 60% of particles are passing through 4.75. That means 4.75 mm we can take now as D60. So if you know the D60 and D10, if we take the ratio of D60 by D10, you will get the value more than 60. So the classification of soil is gravelly silty sand having quotient of uniformity more than 60. And we have 2 more questions to solve, then we can wind up the session of solving the numericals, then we will discuss any further questions. So in the 10th question, the laboratory sieve analysis was carried out on a soil sample using a complete set of ISCs. Out of 500 grams of soil used in the test, 250 was retained and 600, 200 was retained and 500, and remaining 50 grams was retained and 425 mm sieve. So calculate the coefficient of uniformity. So this is what is given. 250 grams retained on 600 mm sieve, 200 grams retained on 500 mm sieve, and 50 grams is retained on 425 mm sieve. So So to determine the coefficient uniformity, first thing we have to know is coefficient of uniformity. Okay. So to coefficient of uniformity, first thing to know is D60 and D10, because the ratio of D60 by D10 is the coefficient of uniformity. So what did I say? D60 means 60% of particles passing through that particular sieve. So now everything is in terms of grams. So we need to calculate what is the percentage. Let us say we have total 500 grams. So in the total 500 grams, let me modify this so it will be easy to understand. Okay. Now this is fine. Okay. How to determine the percentage passing? So we have total 500 grams of soil. So when I say 200 grams is retained and 600 mm, how much is the 200 grams in 500? Let us say 200 by 500. You will get some percentage. In the same way, 250 by 500. You will get some percentage. 50 by 500. You will get some percentage. Okay. So let us say this is a 600 mm sieve. In the 600 mm, 200 is retained. How much is passing? 250 plus 50. Total is 300 is passing. So this 300 is passing out of total 500. So 300 by 500 will be 60%. So through 600 mm sieve, around 60% of the material is passing. So because 60% of material is passing, we can call this 600 mm as D60, and if you take the 500 mm, what is passing? 50 grams is passing. 50 grams is passing divided by out of total is 500 grams. So 50 grams by 500 will be 10%. So through 500 mm sieve, 10% of the material is passing. This we can call it as D10. Once if you know what is, so D60 is 600, D10 is 500, then we can calculate coefficient of uniformity as D60 by D10, which is nothing but 1.2. And this is the last question in the session. While doing the sieve analysis of clay, you found that hydrometer reading is 25 after 35 minutes. So the effective depth corresponding to this reading is 15 centimeters. 50 grams sample was taken for conducting the experiment. Calculate the size of particle corresponding to this reading and the percentage final than this size. Assume that the test was done at the standard conditions. Size of particle should be calculated in mm. Eta or viscosity of the solution is 0.1 points and specific gravity of solids are 2.65. So in the hydrometer analysis, we know this we do for the fine particles. When I say fine, the amount of soil that is passing through 75 micron. Usually it is completely difficult to classify that type of soil using regular sieves. So then we do hydrometer analysis on those soil particles. So the reading is 25. As they have given the reading is 25, we can directly use it because in the question they have mentioned that all these readings were taken at standard conditions. And as a standard conditions, that is at 27 degrees, and they did not mention anything regarding the meniscus and other corrections. So that means this is the finally the corrected one. And this reading was taken after 35 minutes. We know when we do hydrometer analysis, we thoroughly mix the soil with the dispersive agent and also the distilled water thoroughly, and we keep it there, and we assume that at initial stages at t equal to 0, all the layers have a uniform distribution of soil particles, thereby the specific gravity or density in the each layer is constant. As the time progresses, the heavier particles try to settle at the bottom. Thereby, we could observe a difference in the density or specific gravity in each layer. Thereby, we used to take the readings at each set of interval. Here, the reading whatever is given is at 25 after 35 minutes. Okay. So, corresponding to this reading 25, there would be some effective height. So, this effective height usually we get from the calibration chart. Here they have mentioned it as 15 centimeters. So usually this reading and the effective height is corresponding to particular particle size. We do not know which particle size. So for particular particle size, when you take the reading after 35 minutes, it will be 15 centimeters is the height. So what is the particular particle size? That is what we have to calculate in the first part. And it is also mentioned that they have taken around 50 grams of soil to conduct this test. So to calculate this particle size, we can use this Stokes law equation where we know terminal velocity equal to. So you can see here time is given, reading is given, effective depth is given. What is the particle size we don't know. And if we know that particle size in the given 50 grams, how many particles are finer than this particle size? That is second part. So viscosity is given and specific gravity is given. We know the terminal velocity, we can rewrite as effective depth by time equal to d square by 18 mu. This mu is the viscosity given. Gamma s minus gamma w, where this is the unit weight of solid particles and this is the unit weight of water, which you can take as 9.81 kilonewton per meter cube. So in this equation, we know everything except the particle size capital D. So let us substitute the remaining things and calculate the capital D in mm. So you can substitute 15 centimeters as mm, 35 minutes into 60, so it would be in seconds, and 18 into 0.1, so all these things. How do we calculate the unit weight? If you know the specific gravity equal to unit weight of that solids by unit weight of water. Then based on that we can calculate the particle size. So you would get the answer in between 0.027 to 0.029. Okay. So this is the particle size. So for this particle after 35 minutes, we can observe the reading as 15 centimeters, effective depth or the hydrometer reading are as 25. So in the 50 grams of soil, how many percentage of particles are finer than this 0.027 mm? That is the second question. So you can see the formula here where it involves G by G minus 1. We already know the specific gravity into RC. RC is nothing but the corrected reading. We already know. By weight of the soil we know 50 grams. If we could substitute this, we will get the value in between 80 to 81. Okay. So these are the probable questions as far as the numerical solving is concerned. We still have the scope for more conceptual discussion. But as far as the numerical is concerned, in regard to these questions which we have discussed, if you have any further question, you can still post in the forum that would be discussed. And if you want me to go a bit slow or if whether this phase is okay or not, so you can still let me know. So from the next session, we'll try to improve that and include. And in addition to that, in the next live session, we'll discuss the assignment 1 question. So usually for this recording, when we have done with the live session with the participants, the volume has some problem. So that is the reason why I have re-recorded this session again. Because yesterday's session, when I have recorded in the Google Meet, there was a discussion with the participants also. So where the sound clarity was not so good, so I have re-recorded this session so that those participants who couldn't able to join the live session, I thought they can make use of this video to further follow. Now, so from the next week live session, we would be directly recording that Google Meet session only, so that the discussions which we have made during the live session will also be available in the recording. Thank you.